So let's do a little recap. Right? So the underpinning thing with vector search and vector embedding is this thing, a vector. So just like what we have along the bottom of the screen here, it's a series of numbers which represents different dimensions that have been created by the embedding model. And the embedding model is like a neural network that has been designed on a particular set of data, and it can identify these vectors. And for data that's kind of similarly related, we'll end up by getting similar numbers being outputted. Okay. Now, for these embedding models and these kind of vectors, you don't generate the vectors yourself. You're going to use the embedding model. And as I've mentioned in previous videos, is that, there's various different open source, there's paid ones, and you can go along and kind of create your own. So the output from these embedding models is this vector. And this is the bit that you want to, or you'll need to load into your database. Now, different embedding models have different number of dimensions. So it's a little bit of kind of, the Indiana Jones, choose wisely. Is that, size is important, because the greater number of dimensions has two impacts. One is that the larger the vector, which means we have more data to store, more space required to do that. Index space increases, search time increases, time to calculate the distance measures increases, which is effectively the degree of similarity on it. But the more dimensions we have, the better the similarity match, so fewer mismatches. Now, we can always have mismatches, and we'll look at some aspects of that in the next video. But, the more we have, the better it can be. Now, an awful lot of the dimensions that we have is that, here's, the number of dimensions that we have across some of these different embedding models. And if you kind of look at some of the ones that are listed here under the few hundred dimensions, these are ones that have been around for a while. But if we actually look down towards the bottom of the screen, what we end up by getting is some of the more newer embedding models can create dimensions of 1024 or up to over 3000. Okay, so some of these are actually quite large. So you can imagine then, the space required to store, the coordinates for 3000 dimensions or 1000 dimensions. This is going to be quite substantial. And we'll see some examples in code in a later video. And it's also the space required to do it, and then doing the calculations, the similarity matches in relation to those. So there is, a bit of work involved in doing this, and there's a bit of computation time involved in doing it. But this is what, the databases are designed to do, and the algorithms behind these are designed to do, and each database will have its own way of being able to process this. So the vector embedding or vector embedding model, right? So there's a few different variations of it. It's the neural network that generates the vector as the output from it. So it takes as input the kind of the unstructured data. It will apply the model to it and being able to produce the vectors or the set of dimensions that we actually have for it. So what we have here with the cat and dog, this is something in three-dimensional space. So here's the values that kind of correspond to that. But if we went to 1000 dimensions, it's going to be substantially longer. And when we start applying this across, all our different data, we can start finding, not just text like individual words like cat and dog, but we can actually have sentences and paragraphs and whole documents or images. We can actually find things that are actually kind of related in relation to it. Okay, so even if we end up by having it within text, maybe things that are spelled slightly differently, or we have, UK English versus American English, the spellings of it, those will actually be mapped into being kind of similar, related into all of this. So what we can do is, if we have these models that are designed to be able to work across all these different data types, we can have that kind of commonality there in producing the vectors and hence the similarity matches across all of these. Now, one of the questions that comes up a lot is, where does the vector actually comes from? So if we take your typical neural network kind of a diagram is that, typically, or in some cases, is that it's the last layer of the neural network that produces the vector. Okay, so it's not producing the combined output to make a decision. We're taking the values from the last set of layers within that. And from there, what we can do is we can map these out. So here what we have is known as like 3 clusters of data within our kind of 2-dimensional space. And what we end up doing is we just take the points and we just plot them out. So this is where we can start looking at even within the kind of these kind of clusters or groupings, we can see there's even subclusters within that. So we can see strawberry, raspberry, blackberry are kind of closer together and further away from plum, apple, and pear. So these are kind of bushes versus tree fruit. All right. And then we can get into looking at, other things to do with states or different types of animals. So we get to be able to compare all of these in relation to it. And, because, kiwi is, a bit different to, our typical tree fruits and our bush fruits, is, that's why we get to see it's kind of separated out. And if we have a look at the animals, we see the elephant, well, it's a bit different to all the other ones that we've actually kind of listed there. So when it comes to the embedding model, is that, well, we can take that set of diagrams or that kind of 2D model that we have on the left hand side, just what we had in the previous slide, and we can start doing what's known as vector searches. And within the vector searches, we can see is like, so if I have something like I'm searching for a dog, we can start doing searching. So we can see dog is kind of more similar to a wolf, more similar to a puppy, but less similar to a kitten, cat, lion, and elephant, right? Because of the distance measure within that. Now, there's different ways of measuring the distance. There's kind of one that's very common across, pretty much all kind of vendors. And there's a few others that we can get into. Now, when we start talking about, vector search and kind of nearness, sometimes what we end up by getting is this kind of slight incorrect answers sometimes. And this is where we end up by going across clusters. Now, there's ways to overcome some of this, and this is something the topic for another day, but we'll get in here. So we'll get to see where we have dog, puppy, wolf, cat, but we also have California. So this is a way, they're kind of closely related, but, we end up by sometimes by crossing over into another kind of cluster, we end up by getting incorrect information, but there's ways to avoid that. So when we go about kind of searching this data, there's a bit of maths involved, right? And I'll give you a bit of an indication of the type of formulas that are involved in the searching in the next video. But when we start kind of searching across all of these, is that we are trying to find, what is kind of the distance on it? How close or not are they? So if something is close, then they are, related in some sort of way, or they have something in common across all of these. So when we start looking at this, is that this idea of finding things that are closest is known as like our k nearest neighbor, right? So if you've kind of come across that in machine learning before, it's a very similar idea. We're trying to find what are the related items on it. And, when we're in n-dimensional space, this becomes a little bit more complex. But when we start looking at this, we can also start seeing the nearest neighbors. We can actually order them based on how close a particular item is, based on what we're actually looking for. So these kind of distances are a way of us being able to rank them and being able to say what is more, if we have 5 results coming back, we can order them based on closeness. So the first one comes back is the closest in meaning to what we were searching on. The second one is it's a little bit further away. Third one is a little bit further away. Fourth one is a little bit further away, and so on. So when we go about kind of doing all of this, is we get to find what are those kind of relative distances across all of those. So vector search, there are a number of different algorithms out there to be able to help you to do this, and a lot of them are kind of, if you've done some math or machine learning type courses before, some of these terms will be kind of very similar or very familiar to you. So the most common one that's being used is kind of cosine similarity. Euclidean distance, and then we have Manhattan and Hamming and dot as a way of being able to find other kind of similarities. They're just trying to find, as based on these different vectors, how close or not are these vectors to one another, and also based on how long these particular kind of vectors are in relation to all of that. Now, one of the kind of the key things to look at or kind of keep in mind with looking at these distance measures is, the technical details, the maths behind it is, for some it would be really interesting, fascinating. The reality is, well, it's a function, right? Somebody else has coded it up. You assume it's done right, particularly in commercial type environments. It has to be done right and is extensively tested. So you can just use it as a tool. So just like in Excel or any other product, like, if you take your sum function, your average function, your standard deviation function, it's just, well, it's a tool that you can actually use to be able to solve a problem that you're actually dealing with. So in the following examples, I'll just go through at a high level what these are, what they do, and how they're kind of different from one another.